we are, we're back. It's the physics video lecture once again. Physics 107B, video lecture 18. Let's see, where were we? We're talking about potentials and fields, and I'll go ahead and write up what we had ended with last time, then we'll work some examples. So when we, let's see here. Yeah. So potentials and fields. And of course, we can get the fields that we want from the potentials. So the B field is the curl of the vector potential, and for the E field we have minus the gradient of the scalar potential, but it's also tied into the vector potential minus dA dt. Okay. So those are E and B vector. And then the question was, how do we get the vector potential and the scalar potential? Well, they satisfy, so here's like a number of things. These potentials satisfy a wave equation. Potentials and that is an inhomogeneous wave equation, but I'll just write wave equations and write them down. So you've got del squared V minus mu naught epsilon naught, which is just the inverse of the speed of light squared, d squared V dt squared. So that's minus your density, charge density over epsilon naught. And you have the same equation for the vector potential. d squared A dt squared equals minus mu naught times the current density J. Okay, of course, in vacuum, then you just have the wave equations that we've of course worked with before. So good, potentials satisfy these equations, and the solution to these equations, which I'll write down next, are modified, well, let's write them down. Solutions we have V and the vector potential A 4 pi epsilon naught integral. Now, you know, we had rho d volume, but let's leave some room for the argument in terms of the retarded times. So we had a rho, well, let me say, well, what we did there, we had the static form and we generalized it to a form that takes into account and solves for the time-dependent case as well. So that's actually pretty satisfying. So we had rho of r prime and t sub r, where I'll define that retarded potential d tau prime, r minus r prime. And here we had mu naught over 4 pi integral j, again, r prime t retarded d tau prime, also r minus r prime. So obtaining this form is really nice because it seems like just an extension of the case that we had worked with before. Of course, we're going to see there's a lot of complications stuck in here. But so far, that's what we have. These did solve these equations up here with t sub r is equal to t minus script r over c, and this is r minus r prime. Okay. So yeah, when you take your gradients and stuff, you end up having to deal with these slots as well. Good. So that sets us up for an example. So we actually have to take a situation with a charge and current density and calculate these two integrals. And having done that, then we can get the fields by those standard expressions there. Good, I think we have everything. So next, an example. So what we're going to have is a wire, so straight wire with the current that gets switched on at t equals 0. So I of t is equal to 0, t less than 0, and I sub 0, t greater than 0. And we're just going to, I'll draw my picture right here. So we're going to be along a z-axis. The current here, we'll make it red, it's going to be right along the z-axis. Just a linear current. And what we'll do is take some point here. Clearly we're going to have cylindrical symmetry, so we'll use cylindrical coordinates. And not only is it a straight wire, it's going to be a neutral wire, so it's carrying a current, but it has no extra charge on it. So use cylindrical coordinates, wire is neutral, charge neutral. That being the case, the potential is identically equal to 0, but there is an E field because we're going to calculate the vector potential and take its time derivative. This is a nice example. Neutral so that V is identically equal to 0. So I can also draw on this point. So now we're using cylindrical coordinates. So this is a distance S away from the wire. And if I call this a point Z, and the current starts at t equals 0, then the effect is felt here at point P here, point P. The effect is only felt after a finite time, right? So C times T less than S, there's nothing going on, okay? Then A is just identically equal to 0. Only when C times T is greater than S, room here will set this up. Okay. So if C times T is greater than S, then here we'll have a hypotenuse here. Right, then this will be our C times T. So we'll have C times T greater than S, then we'd have S squared plus Z squared equals CT squared from our picture there, and we can solve for S. Okay. Oh no, we solve for Z because Z is going to be the boundary of our integral. So then if we have Z equals root CT squared minus S squared, and absolute value of z less than or equal to ct squared minus s squared. That defines in the positive and negative direction the extent of this current that is actually affecting us in the calculation of the vector potential. So now we can do that. Okay. So this gives the part of the wire that can affect point P, which is a point R. Yeah, I should have written the arguments in here. This is A of R and T. That R right there, T is built into the. Let's just go ahead and put that here. Okay, so we're going to do this integral. We don't have to do the v, right? That's identically equal to 0 because we don't have any charge, but we do have current, and current density times volume. Okay, so that's just going to be I dz. Good. Yeah. So I can set this integral up and see what we get. I'll just write it down. So translating that up there to cylindrical coordinates, we're still numbering things. Oh, we lost it. 4, 5. Now A of S and T is going to be the z component, so we have mu naught over 4 pi. So now we pull out, actually, let me go back a step. Mu naught over 4 pi, pi of T sub R, z hat dz. And there's my r minus r prime. Okay. Good, now I can put the boundaries in. So now we have mu naught over 4 pi. We're going to pull out the I naught. Okay, and we'll pull out the z hat because we're just going to want to deal with that integral. And that integral will be, and we'll take 2 of them because we're just going to integrate, right, we have this right here. Okay, this is the part that we're integrating over. So we'll take a 2 and go from 0 to the upper bound. So that is, we've got a 2, we've got 0 to root ct squared minus s squared. And we've got dz over root s squared plus z squared. Okay. Straight off the construction. Okay. All right, good. So now let's do this integral. Write it down. So we've got mu naught over 2 pi, put the I0 and the z hat, and this is the natural logarithm of the argument plus z, right there, the argument in the form root s squared plus z squared plus z. z. Actually, we're not evaluating it yet, so root s squared plus z squared plus z. And we're going to evaluate that from 0 to root ct squared minus s squared. And we're going to evaluate it and express it as a logarithm of a quotient. And we can see when z is equal to 0, when z is equal to 0, we're just going to get the s, is that right? Yeah, that's a z, sorry. Yeah, when z is equal to 0, we're just going to get the s out there, and that'll be in our denominator. So continuing. So that takes us to mu naught I0 over 2 pi, we've got the z hat, we've got the natural log, something over s. It is, make sure I write clearly, integration with respect to z, so it's root s squared plus ct squared minus s squared plus, and that's going to go away, plus root s squared ct squared minus s squared. And that goes away. I could have simplified that right there. Let's just go ahead and write c times t. And there we go. That's our answer. S squared. Make sure we're good there. 2 pi. Yeah, that's good. So this is a of s and t. And now we want to get the fields. Make sure I got that. Ct plus, yeah. Ct squared minus s squared. Good. So next, 6, we have E is equal to minus gradient V, which was identically 0, minus dA dt. So that's what we have to do now is calculate minus dA dt. Or E is equal to minus time derivative of this. Let's go ahead and pull out mu naught I naught 2 pi. We've still got the z hat. Yes. Z hat, and then the derivative here will have s over ct plus root ct squared minus s squared. And then the derivative with respect to time, still inside here we have c plus 1/2 root ct squared minus s squared, and then the inner derivative 2ct. 2's cancel, and we'll just try to rationalize this and it'll simplify. So let's see here, we can do that. We can pull out a C. Or actually, let's see, we have CT plus C root CT squared minus S squared. Over CT squared minus S squared. And what we'll see is this was in the numerator of this second bracket. It's going to cancel against that one, and we're just going to be left with the S. That S is supposed to cancel. Oh yeah, there's an inner derivative that gave me a 1 over S as well. Yeah, okay, when I just inverted that, I also had an inner derivative 1 over S. I'll put it right there. So those cancel. This cancels against that, and we're just left with this denominator and a CT. So E is equal to, did I have a minus sign there as well? Minus is still there. So my bad, let's see, CT squared derivative with respect to T, so C squared 2C squared T. C. It's right here. This will cancel against that. Good, we have that. Let's write this down. We have minus mu naught I times C, extra factor C there, 2 pi root CT squared minus S squared, and Z hat. So this is something we don't usually see with a straight wire, which I've erased. But notice, this is transient because when t goes to infinity, the denominator grows out out of all bounds, and the thing vanishes. So that's important here. So we have this transient electric field as the current gets switched on. Good, yeah. That was there. And that's the C times T that cancels. There's the extra power of C. Good. So important note, E goes to 0 as t goes to infinity. Good, so that's actually something new here. Now what we want to get, we're going to work on this again in terms of taking the curl. So this was the E field. Next we're going to take the curl and get the B field. Now we kind of know what we're supposed to get on the B field. This is a long straight wire. We're supposed to get the 1 over S dependence when all is said and done. So where's our expression? Actually, we can work with that one up there again. So I'll erase this. And we'll call this 7. We're going to take the curl and get the B field. All right. Make sure we've got the right expression here. Yeah. And notice this was in cylindrical coordinates. So we have to take the curl of this expression and we'll write down the operator in cylindrical coordinates first. So next, B is equal to the curl of A, and that expression in cylindrical coordinates, we'll write the whole thing down. Good to look at. D A Z D phi minus d a phi dz. So that is our S hat component, and we have dAs dz minus dAz ds is our phi hat, and finally we have 1 over S d ds S a phi minus d as d phi. Yeah. Z hat. So the only component that we have going on right now is we have A sub z with respect to S, because this is A sub z. It's the only component we have, and S is in there. So this is what we have to calculate, and then we'll multiply it by phi hat. Okay. So B magnitude will be minus d a z t s. So we'll do that first, then we'll multiply it by phi hat, and that should give us, you know, we kind of know what we're getting because we know we have those concentric circular fields, right? So that has to come out when all is said and done. Let's see what we have now. So dA, so we'll have a minus mu naught I naught over 2 pi, leave the z hat anymore, and the derivative with respect to S, we will have that S over CT plus root CT squared minus S squared. Put that in there. And then we have the inner derivative, which is minus 1 over S squared times that numerator, CT plus root CT squared minus S squared, plus 1 over S times 1/2 root CT squared minus S squared, that's the denominator, and then times minus 2S. So we just have to rationalize this thing somehow, and we'll be good. let's see. We can get rid of all these minus signs. And the 2's are gone as well. And these S's as well. So what do we have here? We have S squared root CT squared minus S squared. And our numerator will be CT root CT squared minus S squared plus CT squared minus S squared, and then from this side multiplying over plus S squared. So these go away, and we can pull out a over S squared CT times plus root CT squared minus S squared. So we get CT factored out, then we're going to have CT plus CT squared minus S squared canceling this one here. We'll have S over S squared, so there's our 1 over S. Yes. Good. So we will have B is equal to U naught I over 2 pi. There's that remnant S there, S squared, S over that S squared. And then we're left with a C times T over a root CT squared minus S squared. And we have the phi hat. Okay, this is really nice. Phi hat. So there's our static solution that we've seen very often, mu naught I, 2 pi s, phi hat, and then we have this time dependence here. It's transient in a different way. For t goes to infinity, large against the s there, this just turns into a 1. Okay. So that's also pretty satisfying. I'll just put that as a note. Limit b as t goes to infinity. I'll put a couple exclamation points there because that clearly turns into a 1, and then we have our good old solution for the straight wire. Okay. So yeah, that's a nice example about the time-dependent potentials. Okay, let's see what's next. Let's consult the clock. Okay, what we want to do next is get started on the potentials for a point charge in motion. That's going to lead into the next chapter in radiation, but we still have a bit to do before we get there. So let's see here. Okay, I'll erase this. Okay, those are nice solutions here, especially there. Okay, what are we going to title this here? So this is the retarded potentials for a point charge in motion. Okay, so next. And so we'll first get the expressions for an arbitrary motion of a point charge. I'll just write a moving point charge. And we have to do a bit of work with these integrals. Let me set this up. Yeah, so I'm going to set up with a couple of designations. So let W of t be the position of our point charge. Point charge will be Q. Q at time t. So now what about the retarded time? So we'll go with the designation we had before. TR is equal to T minus R over C. This of course is R minus R prime. And you can write R minus R prime magnitude is equal to C times T minus TR, right out of this definition here, right? R is R minus R prime. But now we're looking ahead to our integrals where the volume element d tau prime over the point R prime, and that point is actually going to be our point charge. So we can make a substitution in here with the R prime. So our moving charge is considered to be at that R prime. Is located at R prime. So that generalizes this. We're just going to write R minus W of T sub R. So star here generalizes to, got room minus 1, R minus W of T sub R is equal to C T minus T sub R. So T sub R now appears twice in here. and therefore that you could say it's implicitly defined. Okay. This we can also name yeah. So we will be using this script R here being equal to this, R minus W a piece of R. And I needed that. Yeah. This has to be it. Let's do this. This is a vector. Okay. Without the arrow sign, it would be the magnitude I just had there. W's got a vector on it. How did I miss that? It's up there. And this is the retarded position. So yeah, we're going to take this formalism into our expression for the potential and the vector potential. Okay. So let's go ahead and write these down. These actually have a bit going on with them. R and T. We can pull out this magnitude R out of the denominator, but we can't pull this here. This is R prime T sub R d tau prime. And that's, I'm going to do that actually later because I want to move through this quicker the first time. But this, we can't just say rho d tau is equal to the charge the way we'd like to. Okay. And the reason is that down in the denominator it just is a point, so we pulled it out. But up here, it plays the role of an extended charge distribution. So you actually have to get a general expression and then take a limit on it to a point first or afterwards. Good, so that's still right. I just pulled the R out there. That is this object right here now, or its magnitude, just so we know. And for the vector potential, A of R and T, we're going to have mu naught over 4 pi. Now, I skip through here. Yeah, mu naught over 4 pi, and instead of J, I'm going to write rho R prime T sub R times V of T sub R d tau prime. Okay, so that's my current density. Okay, check that out. That's the current density, and I can pull out the R here, which is once again, which is this one. I can pull it out of the denominator there. But in the numerator, I have to do something with this. Okay. And I can pull the V out as well. I think I'll pull it out in this expression already. Yeah, I'll pull it out right here. Integral, because it makes a really interesting point that the vector potential and the scalar potential are really closely related here. Okay, they can be expressed in terms of each other. In fact, let's take another step here. So this mu naught, I can multiply top and bottom by epsilon naught, okay? And then I'll have a 1 over c squared, right? Mu naught epsilon naught is 1 over c squared. I'll put it top and bottom, so I'll end up with 1 over 4 pi epsilon naught c squared r here v and then I've got that self-same integral that we have up here, rho of r prime tr d tau prime. Make sure I made my point right there. C squared, very good. Yeah, so what's the difference between these two? V over c squared. V over c squared, otherwise these two are the same. So let's take that as a preliminary interesting result. So we have A of R t is equal to V over c squared times V of R and t. Okay. Of course, this V in terms of the retarded time and so forth. Okay, so what we finally have to do is discuss this integral here. I'm just going to write out what it is and then leave the discussion of that for next time, just so we'll get the complete expressions here. Because there's a bit of an argument involved, and I want to go straight to these expressions here. So let's see. The integral r prime t sub r d tau prime. Now for our point charge, remember our point charge in motion is just q over 1 minus r hat vector dotted into v divided by c, and that can be simplified across, c q times c over c minus. So we'll do that in a moment. Leading to so with all the designations that we have up here, let me go ahead and write this down, and we'll derive this next time. Q C 4 pi epsilon naught 1 over R C minus vector R. This is a unit vector. This is the full vector, vector R. So that's why we multiplied this R into this expression right here. Dot V. I'd say that's the compact form, but of course there's a lot going on in the arguments here. So that's V. And as I just wrote up there, A is equal to V over C squared, capital V vector. So let's put a box around these. So I owe you the proof of this, the discussion of this. And these are the, and then we'll have these potentials fair and square. They're called the Wiener-Vichert potentials. Potentials. Good, we're going to leave it at this. So this is a good point to have arrived at. This discussion will do as well. These are the potentials with which we can work our way up to radiation in the next chapter. We'll do it. We still have a bit to do in this chapter on these as well, though. So again, potentials for a moving point charge, the motion of the point charge. I've erased it. Yeah, it's up in here, right? There's the W of the retarded time. That should be a vector on top of there, by the way. It's got a vector up there. Okay, good. Leave it at that, and see you guys next time.